In this second tutorial, we will be graphing logarithmic functions. So if we flip over to this part of our notes, we're in the second half of section 4.4. Now we're starting to graph our logarithmic functions. We already talked about logarithmic functions being the inverse of our exponential function. That means if f of x is our exponential function a to the x, then f inverse of x must be our logarithmic function log base a of x. Those are our inverses. Okay, since we know that they're inverses, the domain of the inverse becomes the range of our original function. And the range of the inverse is the domain of our original function. Remember, with inverses, you swap the x and the y. So the entire domain gets switched with the entire range. If you look at any one of our exponential curves, the exponential graphs that we've already been graphing, those generally look like this exponential curve. The domain was all reals. So that means that for our logarithms, the range will be all reals. And again, if you look at one of the exponential curves, the range was a restricted thing. It depended on where the horizontal asymptote was. So since the range was restricted for this function, its inverse, its domain will be restricted. And in this case, since we're just using an x, we know that the domain has to be any positive number from 0 to infinity. X, or this part of the logarithm, is what matters for the domain. What can we plug in for x? Well, x has to be any positive number. And we'll talk about that when we talk about our vertical asymptotes, when we graph. Okay, so what I'd like to do is start by graphing one of our exponential curves that we've already graphed and compare that with the graph of the logarithmic curve. And I'd like to do both of them on the same graph patch. If you have two different colors, I think that it might help. I'm going to graph our exponential curve with red. So it's 2 to the x. We've already graphed this before. We know that the original HK is still 0, 0. And I'm going to put a horizontal asymptote right through that little box that we've created. Start plugging in. We know that the 0 power makes a 1, and the first power makes a 2, and the second power makes a 4 because 2 squared. The reciprocals, the negative exponents, make reciprocals 1 over 2, 1 over 4, and 1 over 8. And there's our exponential curve. There we go. Okay, that's what we had learned already in a previous tutorial. Now let's talk about how to graph a logarithmic curve. Now I know that I can plug in anything I want for x, well, as long as it's a positive number. But much like when we're graphing something like a square root function, we don't want to just plug in anything for x. If I were, graphing a square root function, I'd like to graph or plug in a 1 and a 4 and a 9 and a 16, perfect squares. So when I'm graphing a log base 2 function, there are only certain inputs that I really want to see. I would love to see the log base 2 of 1. I know what that's equal to. I would love to see the log base 2 of 2. I would not like to see the log base 2 of 3 because I don't know what 2 has to be raised to get 3. So I'm going to skip 3 and go to a 4. I would love to see the log base 2 of 8 because I know what 2 has to be raised to get 8. I'm probably finished there, but I like some fractions. I would love to see the log base 2 of 1/2 and the log base 2 of 1/4. We want to be intelligent about what inputs we're putting in for x so that we can graph these. Okay, so h is still a 0 here because there's nothing being subtracted or added to the x, and k is a 0 because there's nothing being added or subtracted to the logarithm, so the same place for the box. We're going to find that there's a vertical asymptote for logarithmic functions. And I'm going to put that right through the box. Now don't be confused that I'm graphing two different graphs on here. That's why I'm doing two different colors. Okay. So what we're doing now is inputting away from my box. We're inputting, that's in the x direction. And let's see what I'm going to input. I'm going to input a 1 first because the log base 2 of 1 is equal to 0. So when I input a 1, that means go to the right 1 unit from my box. I stop and I put my 0. You can see that it's exactly the inverse of what we did with the red function. We stopped, we inputted a 0 and went up 1. This time for the logarithmic, we go over 1 so that we can so we can output the 0. Let's go to some more. The log base 2 of 2, I like that because that's equal to 1. So that means that when I input a 2, I output a 1. Remember, my input is right here, and my output is right here, my y. So if I input a 2, that means, going to the right 2 units from my box, I output a 1. I get to go 2 units over because that's the first power. My next one is a 4, and I know that 2 squared is equal to 4. So that means when I input a 4, 1, 2, 3, 4, I get to go up to the second power. And if I go back to the box, the next one, I'm not really going to do it, but I know that if I inputted an 8, I'd get to go up to the third power. And then back to the box. And then if I wanted to input a 16, I'd get to go up to the fourth power. It's the inputs that are the powers of 2, 1, 2, 4, and 8. But don't forget about your little cheat points. We didn't do this one, the 3. But don't forget your little cheat points. 2 to what power has to be 1 over 2? Well, that's the negative 1 power. So that means when I input a 1/2, I get to go down to the negative 1 power. And 1/4 would get me down to the negative 2 power. So our cheat points are now down in here, inputting a 1/2 and a 1/4 and a 1/8, and you can see that we're not going to be touching the y-axis. That's why there's a vertical asymptote there. And there's our first logarithmic function. So the numbers that we're using are still the powers of 2, 1, 2, 4, 8, 1/2, and 1/4, but instead of like in exponential land, instead of inputting exponents and outputting the powers, in logarithmic land, we're inputting the powers and outputting the exponents. It's exactly inverted. And you can see that these two graphs, which is why I wanted to graph them on the same graph patch, are exactly symmetrical around y equals x. Remember, inverses are exactly symmetrical around y equals x. And you can see any one of the ordered pairs that's on your red graph, for example, this one right here, 2, 4, you just swap the x and the y and you have 4, 2. And you have its corresponding point on its inverse. And you can do that for any of the points. You could do negative 1, 1/2, switch that around, you got 1/2, negative 1. You can see its counterpart. Let's talk about the blue graph. Now we're just talking about the blue graph, which is why this information is going to be right underneath g of x. Let's talk domain and range first. The domain is restricted because we have a vertical asymptote. We've cut the domain well, I don't know about infinity in half, but the domain only exists on this side of our vertical asymptote. So that's just 0 to infinity. The range, on the other hand, now we're pointing all the way down to negative infinity and all the way up to positive infinity. It looks like it might start, tapering off, but it will always be increasing forever, forever, forever. So all reals for the range. Let's do our x-intercept and y-intercept. In this case, we have an x-intercept. I see it right here. It's 1, 0. You might just say 1. I like to put 1, 0 just to remind me that the 0 power creates my 1. My y-intercept, on the other hand, does not exist. We don't have one. If I'm talking about increasing, decreasing, or constant, we know that this is an increasing graph. Look at this blue graph. We are increasing, 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 increasing the life of the graph. So that means since we're only increasing, this graph also is 1 to 1. We talked about that with the exponential curves, which is why if you take the inverse of an exponential curve, which is 1 to 1, you get a function as the inverse. And that's also 1 to 1. Each one of them passes vertical and horizontal, so we do have functions for both. How about the vertical asymptote? In this case, we do have one. It's x equals 0. And basically, it's the first point that's the first value that's restricted in the domain that repeats itself as the vertical asymptote. The horizontal asymptote, of course, we don't have one. None or null set doesn't make any sense. And I'd like to talk about one of the end behaviors. Obviously, as x grows larger, the function grows larger, so I'm not really interested over there. As x approaches infinity, y approaches infinity. Great. Let's talk about this end. Now, we can't go all the way down to negative infinity because we're only getting to this vertical asymptote. So we have to describe what's happening at this vertical asymptote. That's sort of like that middle behavior. So as x approaches that vertical asymptote value of 0, from the right side. In fact, this is the only side we're approaching the vertical asymptote, but it's definitely from the right side, so we use a little plus sign. G of x, let's see what's happening. As we get to the right and start approaching, getting closer and closer and closer to this vertical asymptote in the x direction, the function is pointing all the way down to negative infinity. So that's a little asymptotic behavior. So let's end this tutorial with 3 examples. Let's graph each one of these, a of x, b of x, and c of x. Let's start with the first one, the log base 3 of x plus 4. The first thing I like to find is what is h and what is k. H, again, will always be hiding in here with the x, and it's always that opposite idea, negative 4 plus 4, whatever creates the 0. So h is a negative 4. K is always the number that's out here, either added or subtracted. Since I don't see it, it must be 0. So I know my new starting point is negative 4, 0. I like to go to that starting point and put a little box or some sort of indicator that that's where I'm starting, because that also tells me where my vertical asymptote will be, and there it is. Now the only thing I need to look at in my function is the base. I've already dealt with a lot of the pieces. Well, the one piece that we have. This is shift. Now it's just base 3. I need to know my powers of 3, which are 1, 3, 9. I guess 1/3 and 1/9. Those would be my cheat points, but that's what base 3 is. So what I need to do for my box is go over 1. In fact, all of these are just going to be going over 1 because that's the 0 power. And then back to the box. Always start at your starting point. Now I get to go over 3. I'm going to input a 3. 1, 2, 3. And why do I get to do that? Because base 3 would be to the first power to be 3. So 3, 1. Back to the box. The next one would be 9. Let's see if I can do that. 1, 2, 3, 4, 5, 6, 7, 8, 9. I just do fit it. And I get to go out 9 because that would have been squared. 3 squared. My base squared. I'm definitely not going to do my 27, which would be my next good input. So I'm going to stop there. But I do have my little cheat points here. I get to go 1/3 so that I can go down 1, and 1/9 so I could go down 2. Remember, your negative 1 power and your negative 2 power make the reciprocal of your output. So if you had 3, the reciprocal of that would be 1/3. And you have had 9, you 1/9. And there's our logarithmic curve. Well, just make that point a little bit bigger. There we go. Next one is log, uh-oh, I'm missing something. Where's my base? If you don't see the base, then you know that it's 10. This must be base 10. I'll go ahead and put that in there right now. Let's find h and k first. Negative 5 for h, and k is actually a 0 again. So negative 5, 0. So this time I go 5 units to the left and stop, and there's my box. And so therefore there's my vertical asymptote right through there. Now I need to know that we're talking about base 10. So the powers of 10 are 1, 10, and, well, geez, 100 already. So I'll probably just be doing the 1 and the 10. I guess 1/10 and 1/100 would be my cheat points. Okay, there's only one other thing that's happening here. I see that negative in front. If the negative is multiplied to the entire function, then this is going to flip upside down. It's going to flip upside down. So where we thought we would be going upward, now we go downward because we have to negate all of our outputs. Okay, so here's our box. We go 1 unit from the box, and that would be a 0. And since the opposite of 0 is still 0, that still stays there. Next, we're going to input a 10. I'm going to jump all the way to a 10 because that's the next good power of my base 10. So I'm going to count 10 units over, which is all the way to here. Now, normally, of course, I'd be going up to the first power, but because it's a negative times my logarithm, I'm going to be going down to the negative first power, I guess. I really am not going to count out 100 tick marks. I'd be way off this graph patch. So I'm going to stop right there. And then I'm going to realize that I do have my cheat points. Normally, they would be, 1/10 and then down 1. But in this case, because of the negative, I get to go up 1. And then over 100th and up 2. And I guess 1,000th if you really want to. But I wouldn't get too close to the vertical asymptote. I wouldn't want you to touch that. So this is what a negative logarithm would look like, a decreasing curve. And it's really stretched out because the base is already a 10. Our final example, now we have natural logarithm. Well, that's a base e. That's okay. We just need to remember that e is approximately 2.7, and that e squared, if we need that, is approximately 7.4. I don't know what 1 over e is and what 1 over e squared is, so those are just my cheat points anyway. Let's see what's going on here. My h, this time, since there's nothing added or subtracted to the h must be 0, to the x, excuse me, h must be 0, and k is this number out here, -4. So I'm going to be going 0, -4, and that's where my box goes. I'll put my vertical asymptote right through that box. So now that I have my starting point, I need to know what my base is, which is e, and that weird number, the 2.7 and e squared, 7.4. But there's one more thing that's going on here. This time there's a negative in front of my input. That flips in the y-axis. So I would have thought that I'd be over here, but in this case I flip in the y-axis and I'm actually right here. Right, because the 1, 0. E is about 2.7, so I would have thought to go 1, 2.7 before I could go up to the 1. But in this case, it flips over the y-axis and is over here. So I'm really counting 2.7 this way before I could go up to a 1. The next value that I would have put in is e squared, or about 7.4. So 1, 2, 3, 4, 5, 6, 7.4, so that I could go up 2 units. But again, I'm going in the wrong direction because there's a flip in the y-axis. So it's actually over this way, 1, 2, 3, 4, 5, 6, 7.4-ish. I'm putting that right in there. The cheat points normally would be down in here. You see where they would be. Of course, they're down here now. I know that it's a -1 and a -2 and a -3 as my outputs. I have no idea what 1 over e and 1 over e squared is, but who cares? As long as they're there, then I know that you know that the function is a continuous curve. And this time we're flipped over the y-axis, excuse me, over the y-axis, over this vertical asymptote. And now our domain is over here, which makes sense. Now we can only input negative values, because if I'm going to multiply those negative values by a negative, then I have my regular positives. So this is how we can flip over the vertical asymptote and get values over here. Now my domain has changed. My domain this time is -infinity to 0. Range is still the same. It's all reals. So thanks for watching these graphs, and we'll practice these. Bring some graph paper to class. We'll see you then. Bye-bye.